Beneath a busy city, a massive steel cutterhead is cutting into the ground and continuously carrying excavated soil way behind it. But if the machine removes soil too quickly, the ground in front of it can lose stability, and the street above may begin to settle. If it holds back too much material, pressure can rise beyond the intended level and push the ground upward instead. The strange part is that this machine does not resist the earth with a completely rigid wall. It uses the soil it has, just excavated as the supporting medium at the tunnel face. And to move forward, its hydraulic thrust cylinders must push against the concrete tunnel ring that was just built behind it. This is an earth pressure balance machine, or EPB. It is not simply a giant drill. It is an underground factory that must excavate, control pressure, remove soil, and build a permanent structure as one coordinated process. If the flow of material falls out of rhythm, the consequences can appear at the surface. At the front of the machine is the cutterhead, a rotating wheel approximately as wide as the excavated tunnel. Cutting tools cover its face, while openings allow broken soil to pass through. The cutterhead rotates as the hydraulic thrust system drives the shield forward, forcing the tools into the ground. Immediately behind the cutterhead is not an empty space. It is a pressurized excavation chamber, separated from the rest of the machine by a sealed steel bulkhead. Soil passes through the cutterhead openings, fills this chamber, and becomes the medium that transfers supporting pressure back to the tunnel face. A screw conveyor passes through the lower part of the bulkhead. Inside a steel tube, a rotating screw draws soil from the pressurized chamber and moves it toward the rear. In typical EPB operation, the material gradually loses pressure as it travels through the screw. At the outlet, it transfers to a belt conveyor or another haulage system farther back in the tunnel. A cylindrical steel shield surrounds these components. It temporarily supports the ground around the machine until the permanent structure can be installed. Near the tail of the shield, a segment erector lifts precast concrete lining segments, rotates them into position, and assembles them into a complete ring. Behind the main shield stretches an entire backup train. It carries conveyors, electrical and hydraulic equipment, ventilation, grout systems, lining segments, and the control cabin. What people casually call a boring machine is really a moving production line beneath the ground. The most dangerous enemy is not simply hard soil, it is an imbalance. At the tunnel face, ahead of the cutterhead, the soil and groundwater place pressure on the ground that is about to be excavated. Cutting that material changes the existing stress condition. If the tunnel face no longer receives enough support, soil can move into the excavation chamber. That movement creates a loss of ground volume, which can travel upward and eventually produce settlement at the surface. But simply increasing chamber pressure is not a complete answer. Excessive pressure can push soil away from the cutterhead or cause ground heave. The goal is not to create the highest possible pressure. It is to maintain the support pressure appropriate for the local soil and groundwater conditions. The machine must also keep removing soil while that pressure is maintained. The excavation chamber needs to remain full, enough to transmit support, while the screw conveyor creates a controlled path from the pressurized chamber toward the tunnel behind it. If the screw removes material faster than the cutterhead supplies it, the chamber pressure can fall. If too little material leaves while the machine continues advancing, the chamber becomes more heavily loaded and pressure can rise. The soil itself does not remain constant. Clay may stick to the equipment. Sandy ground may not naturally form a material plug that is tight enough. Groundwater can move through connected voids. Loose excavated soil does not automatically behave like a precise pressure regulator. So how do engineers turn that unpredictable material into a controllable pressure plug while still moving it out of the machine at the required rate? The solution begins with soil conditioning. Water, foam, or suitable additives can be introduced near the cutterhead and inside the excavation chamber. The objective is to give the excavated soil the right plasticity, flow behavior, and sealing ability. It must mix consistently, transmit pressure to the tunnel face, and pass through the screw conveyor in a controlled way. The additives do not replace the soil. They help the excavated soil perform as the supporting medium. The thrust cylinders move the machine forward by bracing against the nearest completed lining ring and pressing the cutter head into the ground. But thrust force alone does not set face pressure. The sealed chamber must remain sufficiently full of conditioned soil. The amount entering and leaving is coordinated so that this material maintains the required support pressure. Pressure sensors on the bulkhead monitor conditions at several locations, because pressure inside the chamber is not necessarily uniform from bottom to top. The screw conveyor performs two jobs at once. It transports soil, but it also creates a controlled pressure reduction path. Soil filling. The screw tube acts as a resisting plug. As the screw turns, the material moves gradually from the pressurized chamber toward the discharge end. Screw speed and the opening of the discharge gate determine how quickly soil leaves the chamber. This means pressure balance does not come from one component. It comes from maintaining a mass balance over time. Advance rate and cutter head operation determine how much soil enters the chamber. Screw speed determines how much leaves. The behavior of the conditioned soil determines how pressure is transferred and reduced between the two ends. Operators therefore watch chamber pressure, cutter head torque, thrust force, advance rate, screw speed, and the amount of discharged soil. Together, these values must be interpreted as one system. Chamber pressure may appear acceptable, for example, while an abnormal amount of discharged soil warns that the machine is removing more ground than expected for the length of tunnel it has advanced. During excavation, the thrust cylinders push against the nearest completed concrete ring. In a typical single shield EPB cycle, boring stops after the machine advances by approximately the width of one lining ring. Groups of cylinders retract to make room for the segment erector. The erector places the precast concrete segments inside the protected tail of the shield and completes a new ring. The cylinders then brace against that new ring for the next advance. But the cutter head must excavate a diameter larger than the outside of the finished lining. As the shield moves forward, it leaves an annular gap between the surrounding ground and the concrete segments. Even with a stable face, soil could move into this gap if it were left open. Grout is therefore injected behind the shield tail to fill the void, hold the lining near its intended position, and limit ground movement. Now, the machine's complete cycle can be followed as one connected operation. The cutter head rotates and excavates. The thrust cylinders brace against the concrete lining and drive the shield forward. Soil passes through the cutter head, is mixed, and fills the excavation chamber. The conditioned material transfers controlled support pressure to the tunnel face, resisting the tendency of soil and groundwater to move inward. At the same time, the screw conveyor removes the required amount of soil and reduces its pressure before transferring it to the belt. The control system does more than hold one pressure reading. It coordinates excavation, discharge, and advance while monitoring how the ground actually responds. The steel shield provides temporary support around the machine. When an advance is complete, the segment erector builds a new concrete lining ring inside that protection. Grout fills the surrounding gap. The thrust cylinders move their reaction point onto the newly completed ring, and the cycle begins again. Three flows move through this process, and they cannot be confused. Material flows from the tunnel face to the excavation chamber through the screw and out along the conveyor. Force flows from the concrete ring through the thrust cylinders to the cutter head and the ground ahead. Information flows from sensors to the control system, which adjusts the machine. Only when all three remain coordinated can the tunnel advance while disturbance to the ground above stays within acceptable limits. That resolves the original paradox. The machine removes soil without leaving an uncontrolled void. At the front, pressurized conditioned soil supports the tunnel face. Around the machine, the steel shield provides temporary protection. Immediately behind it, the concrete lining and grout take over the permanent supporting role. An EPB machine does more than cut a circular opening through the earth. It controls a continuous transfer of load from undisturbed ground to the pressurized soil chamber and steel shield, and finally to the grouted concrete lining. The cutter head creates the excavated material. The chamber turns that material into support. The screw conveyor regulates discharge and pressure reduction. The thrust cylinders use the lining as their reaction point. And the segment erector and grout system convert the newly opened space into a stable structure. That continuous handoff is what allows a massive underground factory to move forward one concrete ring at a time, while its most important achievement is keeping the world above almost unaware that it is passing underneath.